Otakar Boruvka was a Czech mathematician who first designed the algorithm, named after himself, in 1926 in order to design an efficient electricity network for Moravia. It abstracted the problem, allowing the algorithm to be generalized to any MST problem. Boruvka's algorithm is a greedy algorithm used to find the minimum spanning tree of connected graphs, or the minimum spanning forest of unconnected graphs. The latter is done by applying the algorithm to each component independently. The algorithm may only be applied to weighted undirected graphs. Each vertex is treated as a separate component. Initially, the number of components is set to the number of vertices. Then, for each component, the cheapest incident edge connected to another component is selected. In the case of a tie between edges, any tied edge can be chosen. Then, the selected edges are added to the MST, connecting components, thereby reducing the number of remaining components. Then the previous steps are repeated until only one component remains, which is the MST. The algorithm uses a divide and conquer approach. By treating each vertex as a separate connected component and combining them with the most locally optimal edges, a globally optimal solution is found. The principles laid down in Boruvka's algorithm establish the groundworks for future algorithms, such as prims, which build upon it in order to improve the efficiency and potential for practical application. In addition, it demonstrated that abstract mathematical solutions could be successfully applied to real-world problems, which is a key concept in modern computing. Even though parallel computing was an alien concept in 1926, and Boruvka's algorithm certainly wasn't designed with it in mind, the fact still remains that the algorithm is parallelizable by nature and has been able to be used in MST problems of massive scale through the exploitation of this property. I'll now move on to my own implementation. So my implementation it all takes place inside of this class called graph. In the constructor we have a list of edges and a set of vertices. And then each of the edges in this edge list have this function called on it, which would literally just add the whole edge to the list of edges, but also it will update the set of vertices to include the vertices that are included in the edge. So the self.parent, self.rank dictionaries for the union find structure. So to begin with, each of the vertices is its own parent, and then the rank for everything is 0. And then down here, this is where the algorithm itself is actually run, and these are the outputs. And then this is just for displaying some of the output down here. So these are mostly just debug functions. So we have some for visualizing the graphs, and that's about what can be said for that. So here we have the union find structure, or the methods for it. So the find will just recursively find the parent of the node V, which it does by doing the recursive call on the dictionary. The union method, it first finds a parent for each of U and V, and if they're not in the same component, it will continue. Otherwise, it returns false. And it's just whichever one has a higher rank will become the parent, and if they are the same rank, then it's always U, and then U has its rank increased. So here's the algorithm itself. So we initialize the output edges to an empty list, and the weight to 0. The component number is just how many vertices there are, because each vertex is its own connected component to begin with. And while there's more than one component, the cheapest edges is first set to none, everything's set to none for each vertex. And then we loop through all of the edges, U, V, and W being the sort of start, end, and weight of each edge. We find the parent of U and V, and as long as they're not already in the same connected component, we check to see if this edge is the new cheapest edge for that component, or if it's none. Obviously it has to be, because none is just the worst it could possibly be. And then we loop through all of the cheapest edge values, which aren't none, and then we see if we can unify them, each of the vertices, so that makes the edge appear in the minimum spanning tree at the end of it. So then we can reduce, for each one we have successfully unified, we can reduce the component number by 1, and then of course once we do this enough times and the component's number gets to 1, we can output everything, because that's the final minimum spanning tree. So I can just show you it works. So I've got a graph set up. So this is it before we've run Boruvka's algorithm on it, and then here's it afterwards. So we can see that it's, and down here we can see the results in more detail. So it starts off, these are the vertices and these are the edges, and after running the algorithm, it brings the vertices stay the same, the order does change, but the edges drastically reduce, and the total weight becomes 14. So yeah.